In this video lesson, we'll be looking at trigonometry and circular functions. Up to this point, all we've done is right triangle trigonometry, where you're bound by the, the circumstances with a right triangle. The fact that theta, what we would typically work in trigonometry, had to be a value between 0 and 90 degrees. When we transition to circular trigonometry, we're boundless. So we're working within the Cartesian plane, and theta can be any real number, meaning 0, positive values, negative values. So when we begin the transition to the Cartesian plane, we'll look to consider the different ratios that come along with trigonometry. Meaning this, if I had a Cartesian plane, got my angle, and there's theta. If I draw a circle here, I now have this particular point on the circle which has coordinates x and y. Now the value of those coordinates come from how far you are from the origin on the x-axis, how far you are on the origin in the y-axis. And of course, the distance of the angle you first drew would be the radius of the circle. And so it brings my attention to this triangle we have inside of the circle. Well, the y and the x coordinate now wind up being the lengths of the different legs. So the y now represents the opposite side from the angle, x is the adjacent side, and r is the hypotenuse of the triangle. So with these three representations, we now have a new way of identifying our six trig functions. So sine of theta is now y over r, as opposed to just opposite over hypotenuse. We're not using opposite and hypotenuse because we don't have a triangle. We actually have a point on the Cartesian plane, or an angle being made on the Cartesian plane. So sine of theta would be x over r, tangent of theta, y over x, cosecant of theta, r over y, secant of theta, r over x, and cotangent theta, x over y. And there's a certain caveat that comes along with this, that both x and y can't both equal 0. Because if they both equal 0, we'd be at the origin, and there would not be an angle theta. Additionally, r can simply be found by using Pythagorean's theorem. So, if we look at circular functions, we're going to kind of go backwards and evolve into certain things. So secant theta traditionally was the hypotenuse over the adjacent. So if we had to find the secant of 30 degrees, again, hypotenuse over adjacent. Because it's a 30 degrees, we can create our special right triangle, 30, 60, 90. And we can apply the values for sure, 1, 2, and radical 3. So therefore, those values would transition to our triangle. We can now begin to determine what the secant of 30 is. 2 over radical 3. Simplify that, 2 radical 3 over 3. Again, this is building up to what we're about to do. If I had a different one, cotangent, adjacent over opposite. Because if I'm doing the cotangent of 45 degrees, I can create my special right triangle using Scholl, 1 radical 2, and place those values on the triangle. And now we have enough information to determine the cotangent of 45 degrees. Using the adjacent and the opposite, 1 over 1, secant of 45 degrees is 1. So we're going to build upon that. So now we'll transition to a circle. And we're using all of our special angles that we would have had in the unit circle. Previous problem, we looked at secant of 30, which was this portion of the circle. Well, if we looked at a problem like secant of 390, well, 390 degrees happens to have the exact same initial and terminal side, which means 30 and 390 are coterminal angles. So the triangle that we used for secant of 30 will be the exact same triangle used for secant of 390. So therefore, we have the same adjacent, opposite, and hypotenuse, and of course we have the same x, y, and r. So we can conclude the secant of 390 is the exact same as the secant of 30. So from this slide, we make a general conclusion that coterminal angles, they share the same trigonometric functions. So this is what we're going to build upon. So once we understand If I can find a coterminal angle, then I'm actually working with the same situation. So we'll apply that. We have tangent of 960. Well, if we first look to find the coterminal angle, that's within our first revolution. So we'll just start subtracting 360 until we get to our coterminal angle. That's in our first revolution. So 240 degrees. There's the portion we're working with. So we're understanding that tangent of 960 is the exact same thing as tangent of 240 degrees. So I have this point. It happens to be in quadrant 3, so we'll take note of that. Negative, negative. If I projected a vertical and horizontal dotted line, I begin to create this triangle. Triangle happens to have a 60-degree angle here, creating my 30, 60, 90. So we'll apply everything we know about Schul, 1, 2, radical 3, but we're also considering that it's in the third quadrant. So the short side won't just be 1, because it's in the third quadrant, it's actually negative 1. Same with the long, won't be radical 3, it'll be negative radical 3. But the hypotenuse is still going to be 2 because this represents the radius of the circle. So we're combining what we know about right triangles, Schul, and the Cartesian plane. So now we know what x, y, and r will be. So if I superimposed or I took out this triangle, my triangle has values negative 1, negative 3, negative radical 3, and 2. Well, these used to be the adjacent, the opposite, and the hypotenuse, but now they're the x, the y, and the r. So we're ready to answer the question. If tangent of 960 is found by simply y over x, we transition the information. Negative radical 3 was the y, negative 1 was the x. Simplify. Tangent of 960 is radical 3. So when we look back and determine what was it that we needed to actually answer this question, first thing we determined was the quadrant. We found the quadrant where the terminal side was by finding a coterminal angle. Next thing we considered was the reference angle. In this case, it was 60 degrees. That was the transition to go to Schul and our special right triangles. So this is the information that we'll need to find to answer any of these questions. So let's come up with some steps. Evaluating trig functions, theta, that has a reference angle that's one of our special angles. Notice I have both degrees and radians. So the first step was to determine the quadrant. That's where we used the coterminal angle. Next, once we had the quadrant, we considered the signs of the coordinates in that quadrant. Third thing we did, we found the reference angle. Afterwards, we applied everything we knew about Schul, and then we had the x, y, and r to substitute. So let's try a few problems. Cotan 570. First step was to find the quadrant that it's located. So we found the coterminal angle. 210 happens to be coterminal to 570. That puts us in quadrant 3. Step 2 says name the signs. Well, in quadrant 3, negative, negative. Now, next step, find the reference angle. Reference angle for 570 degrees is 30 degrees. Now, this is where I recommend put these bits of information together. So you're going to draw a Cartesian plane, and I would recommend drawing a 30-degree angle in quadrant 3. There's your 30-degree angle in quadrant 3. So you can begin to visualize the values that you're going to put. So Schul, when we create our triangle, Schul tells us 1, 2, radical 3. But because we're in the third quadrant, negative 1, negative radical 3, and 2. So we now have the three values for x, y, and r. So we can answer the question. Cotangent of 570 is x over y. Substituting those values, there's our final answer. Next one. Now we're using radians. Step 1 is still the same. So my recommendation, there we go. We found our coterminal angle, 3 pi over 4. Next is to find the coordinates, the signs of the coordinates in quadrant 2, negative, positive. Our reference angle here would be pi over 4, and pi over 4 just happens to be the same as 45 degrees, which help us to convert to our special right triangle. So I will draw a 45-degree angle in quadrant 2. When I project my triangle, I can begin now to transition from shoal to the values here. So my short, so here both the legs will be 1 unit, but because I'm in quadrant 2, -1 for the horizontal, 1 for the vertical. So now we know the values of x, y, and r. Substituting that into cosecant, r over y, radical 2 over 1, radical 2. All right, I believe this is the last situation. So tangent of -11 pi over 2. First step, let's find the coterminal angle. The coterminal angle happens to be pi over 2, which happens to land on the y-axis. So it's not in any of the quadrants. So we have a very special situation here to land the terminal side on an axis. So let's draw this out. If we have pi over 2 on our Cartesian plane, and let's just say this was the terminal side. If I put a point here, that point will have very specific coordinates because it's on the y-axis. The coordinates, 0, and some value for y, like a y-intercept. And so if I was to, so we at least know right now, out of the 3 values we need, the x, the y, and the r, guaranteed we know the x is 0 and the y is some number. Don't know quite what it is. What we don't know is the r. But if r stands for radius, it makes sense to draw a circle. Now we can see the radius of this circle is the exact same as the y. So now we should have enough information to determine the tangent. If tangent is y over x, we know y is some generic number, but x is 0. So we have a very specific ratio. But any number divided by 0 happens to be undefined. So our answer here is actually undefined. So from this slide, we begin to make some generalizations about the terminal side being on an axis. So if the terminal side of an angle is on an axis, the trigonometric ratio will be one of 4 possible answers. So there won't be any need to do any shoal or any special right triangles. Your 4 possible answers will either be 0 over some number, which equals 0, some number over 0, which we just saw was undefined, or a number over itself, meaning you had the r, the radius, and the y could be the exact same number, which is 1. And the last possibility is a number over its opposite, meaning if you were in the bottom section of the y-axis, then the y-coordinate would be negative, but the radius would still be positive. But both of them would be the exact same absolute value. So you've been presented with all the different possibilities for finding trigonometric functions of angles much larger than or other than a value between 0 and 90. So hopefully this helps.